So welcome back everyone to the second video of the course Advanced SQL here at the University of Tübingen. Welcome back. This is just a brief video to bring us up to speed on the notions of the basic notions of the relational of the tabular data model that we are going to work with, just so we use all the same vocabulary and the same notions when we talk about tables and attributes and columns and so on. But first, a few words on the relational database system that we're going to use in this particular course. It will be PostgreSQL. I'm using a particular version here, 12.x. Let's see whether this works. Here's my installation of PostgreSQL. I can start PostgreSQL shell. As you can see, let's see whether the system operates okay. 42 looks good to me. All right, so this is PostgreSQL, my PostgreSQL installation. I urge you to have your own PostgreSQL installation to follow this course. Actually, I think it will be not possible to follow this course without your own PostgreSQL installation, because we want to get our hands dirty and really write SQL, understand SQL, experiment with SQL. So please install a version of PostgreSQL. It doesn't have to be the most recent version like 12.1 I've installed locally here on my machine. Probably any version 11.x will work okay. To follow the details of this course. It should be really straightforward and easy to install on your Mac OS, Windows or Linux boxes. It works straight off the box on most of these systems. For some of these systems, you've got one-click installers to get up and running with PostgreSQL. PostgreSQL is the very best fit for this particular course because it implements an extensive dialect of SQL, the very recent SQL 2011 dialect that I was mentioning in the very first video. PostgreSQL is really complete and really advanced in this particular aspect. PostgreSQL is generally awesome. It's extensible, it's inspectable, it makes it a perfect vehicle for database research, but also for this particular course. So please, everyone, install your own copy of the PostgreSQL database system. Thanks, a big kudos to the PostgreSQL developer community to build such an awesome system for many, many years now. Okay, so as I told you, let's review a few basic details of the tabular data model, of the data structures that SQL operates over. I will not provide a full introduction to the tabular data model in this particular course, but let's review some basic vocabulary here so that we can speak the same language in this course. We will do the same with the SQL language itself. So we will have upcoming videos on the fundamentals of the SQL language that allow you to follow the initial examples, and based on these fundamentals we will build our advanced uses of SQL. Let's see how we can work that out. All right. So SQL operates over tables. All data in a relational database system is held in tables. There is no other way. Tables are the data structure, the only data structure. All right. Tables are organized into columns. This particular table has 3 columns, the A1, A2, and A3 column. Columns are named, and columns in such a table are organized in left to right fashion. So A1 is the leftmost column, this is the second column, A3 is the rightmost column. It makes sense to speak of the leftmost and the rightmost column in such a table. The table head A1, A2, A3 is ordered in a sense, you could say. This is different for the rows of this particular table. The instance where the data lives. We have particular rows that hold the data in such a table, and this might be the row I and this might be the row J, all right? But it doesn't make much sense to say that row I comes before row J or row J is after row Y. There is no order on the rows of such a table. If you find yourself formulating queries that rely on some notion of ordering of rows in such a table, then that sounds fishy to me. There is no notion of order of rows in such a table. It's a bag of rows. A bag of rows. There might be even duplicates. We can talk about this in a minute in such a table. It's an unordered bag of rows. This is the data structure that we will be operating over. There is actually not much else. Very awesome. So a closer look at the data that is actually stored in such tables, the cells, as you would call them. This is one cell of this particular table, the value J1 cell. In row J, in the very first column, we find value J1. We call this particular value one cell of this particular table. The columns in such a table are typed. This is column A1, and it will be assigned a type tau1. That's what I'm depicting here. You can see I am abusing the symbol type of that is used in many programming languages like Haskell, for example. So the column AI has type tau-y. That means all values, all cell values in this column A1, for example, will be of type tau1. It's a homogeneous column. There can't be booleans in one row and integers in the next. All values in the column A1 agree on their type tau1. All right, so we are talking about type tables in this particular data model. Some of these values might be null. Null means that this particular instance of the table has no specific value for this particular cell. The author of this particular table inserts null whenever he or she is unsure about the content that should be placed there, or if there is no applicable content that should be placed there. We will find many uses of null. Actually, the semantics of null is a bit whooshy and a bit unclear, but there are many good uses of placing null in particular cell values to indicate that no specific value applies. Okay, if we are sure that a particular column will never carry null values, we can say so when we create the table. When we create the table, we assign types to these columns, and we also say, hey, this column will never carry null values. All cells will be filled with specific values. All right. The tables that we are looking at and the cell values that we are looking at are particularly simple. All the tables that we will be working with are in so-called first normal form, or 1NF. This is this abbreviation, 1NF. We are working with 1NF table. That means the cell values themselves, such a cell value here, will be an atomic value. It will have no structure according to the relational data model. We might have a text value there, and the text value is comprised of individual characters, but that doesn't make it structured in terms of relational data model. Such a value may never be a table again, for example. Okay, so from the viewpoint of the relational data model, this is an atomic value. It could be an array comprised of an array of integers, for example. Still, from the viewpoint of the relational data model, that would be an atomic value. It will not be a relational table again. We will have the means to inspect the particular items, the particular elements of such an array, and that's fine. But we will never be able to nest tables into other tables. There are other means of representing such deeply structured data in the relational data model, and we will make do with just atomic 1NF values in these tables. We will see that some of these cell values, for some of these val, j, y, some of these may particularly look like complex values. They might be arrays, as I said, or they might even be JSON data, so deeply tree structured data, but that still doesn't make them atomic values from the viewpoint of the relational data model. No nested tables. If we would have nested tables, as this footnote implies, we would leave the first normal form world, the 1NF world, and we would enter the non-first normal form, or the NF-NF or NF square world. We will not do that in this particular course. There's interesting research and notions that talk about NF square tables, but this is outside the discussion of this particular course. Because the rows in such a table are unordered, how would you identify, how would you point at a particular row in a query or in an application? Or even if you communicate with somebody else about the rows in a particular table, it will not make sense to say, oh, I'm talking about the first row, or I'm talking about the second row or the last row. That doesn't make sense. We have to find other means to identify the rows in such a table. And the answer of the relational data model in this respect is we will use values, particular values, to identify particular rows. Okay, that's where the notion of a key comes from. This table, this 3-column table, has been assigned a key of 2 columns. You see that in these slides I will follow the convention to mark the keys, to mark the key columns of this particular table with these dashed lines here. So A1 and A2 make up the key of this particular table. And the meaning of this is that no two rows agree in their A1, A2 values. Because this is the case, we can use A1, A2 pairs to identify single particular rows. No other row will share the same A1, A2 value, so we can use this pair of A1, A2 values of the particular types, tau1 and tau2, to identify particular rows. That can be used in applications and in queries to pinpoint particular rows. We will not use pointers or references or positions tables. We will use key values. All right. Once we declare A1 and A2 as a key for this particular table, the system will protect us, or will keep us from inserting rows into this tables that agree in their A1, A2 values. That would violate the unique identification characteristic. So we will see many examples where you get error messages if you try to violate this particular key constraint, the key condition that the A1, A2 values have to be unique across the entire table. That is the first point of this particular slide. Because these values are unique, we can use SQL predicates like this to identify single rows. No other row, only one row, at most one row. At most one row will carry value C1 in column A1 and will carry value C2 in column A2, and so that we can use this predicate to identify the particular C1, C2 row. Say, there might be not such a row at all, so this predicate might identify 0 rows, but if it identifies a row, it identifies at most one row. There's a convention when you talk and when you work with such tables that all the key columns are assembled on the left-hand side of this of the table head. So A1 and A2 are the key columns, so they are presented here on the left-hand side of this table schema. But that's just a convention I try to follow, and that most textbooks try to follow, just for easy orientation. Actually, A1 and A3 could be keyed in this table. A3 on its own might be a key for this particular table, so that would be fine as well, but we will try to follow that convention. And for compact notations of table schemas, we will use this particular notation where we just enumerate the attributes in the table head of the table and then underline the key attributes. Okay, lastly, how do we connect different tables together? In this example, we are already talking about 2 tables, T and S. And we want to have an opportunity or the possibility to connect the rows between these 2 tables, T and S. Maybe S supplies some details, some further details for the rows that are held in this table T. And the answer of the relational, of the tabular data model in this particular case, is the use of foreign keys. Foreign keys. Okay. So if we want to connect this particular row J of the T table with this particular row K in the S table, then we just make sure to take this particular key value. You can see it's B1 is a key in the S table. We take this particular key value of the kth row and place it over here. TJ3 is equal to SK1. this condition connects this particular row with this particular row J in table T. So again, the equality of values in this A3 column and the B1 column here is used to establish a connection between these two particular rows. We can use SK1 to identify this particular row because it's a key value. Okay, that fits. We can even connect this row with two different rows. So row I, for example, might also depend on the awesome details in the kth row over here. No problem. TJ3 and TI3 might be the same value, SK1 for example, so both would point to this case row here in table S. That's perfect. That's fine, of course. A3 is a foreign key pointing to table S. A3 is not a key in table T, so the values in this column don't have to be unique. They don't need to be unique. We can share SK1 here, for example, and point to the same row on the other side. That's perfectly fine. A nice thing about this construction is that, again, the database system will make sure that we don't point into nirvana. We will be protected from the presence of dangling pointers. Entering a particular value here that doesn't occur in the key column of table S will be inhibited and by the database system. So we are protected from entering key values at this particular in this particular column that point to nowhere, that point to whatever, to here. That's impossible. We cannot do that. The system will protect us from that. No dangling pointers. So that's actually a progress over the references or pointers in your everyday programming languages. All right. So much for that. These are the basic notions of the relational data model. Let's not expand that here. We will collect all the necessary gory details of relational data model while we talk about SQL itself. You can see that the basic ideas of the relational data model are super simple. Likewise, SQL is super simple. So this will be a course that talks about really simple but very powerful ideas. And I cannot wait to share all the cool details of SQL with you. So take care. See you soon. Bye-bye.